So welcome everybody to lecture 4 of the SNAPP Summer School. Just a reminder that videos of past lectures and lecture notes for past lectures are posted on the SNAPP website on the summer school page if you scroll down to the schedule. And with that, Anton, please take it away.
Thanks, Zeke. Good to see everyone. Um, Let me do a quick recap of what we've learned and then what we're going to talk about today. So I'm going to stick to this page, right? Um, what are the steps? We start with some kind of model, some Markov chain. It has a generator. We perform Taylor expansion on the generator, and we extract one of potentially many or infinitely many diffusion approximations or diffusion generators. And then we said, well, we can look at the difference of the two stationary distributions in terms of the difference of the generators. And that's good because since we've selected the diffusion generator to capture first and second order terms, then the error should depend on third order terms and above, and this should be manageable somehow. Remember that the formal tool for all of this was the Poisson equation. So we start from the Poisson equation of the diffusion, and the generator of the diffusion has two components. It takes a drift B and the diffusion coefficient A. Okay. So we set up the Poisson equation. We use the BAR to write down the difference between X and Y in terms of the difference of the generators. And then once we actually zoom in on this error, we see that it depends on two things. So for example, let me highlight term number 1 here. Term number 1 has some kind of expected value of the first moment and how big is the second derivative. And I gave these things names. So we're going to have to bound the derivatives of the Poisson equation solution. And these are called gradient bounds or also Stein factor bounds. And we need to bound the moments. Now, at the end of the last lecture, I showed you how to bound the moments using a Foster-Lyapunov drift condition. And today we're going to be talking about these Stein factor bounds or the gradient bounds. This is really um, this is really where all the know-how is needed to apply the approach. In other words, prior to this step, we really didn't go very deep into any technique, but now we have to. Okay. Um, a few things. Number one, what does the potential function or the solution to Poisson's equation depend on? It depends on the form of the diffusion generator. What does the form of the diffusion generator depend on? It depends on the drift and diffusion coefficient. In other words, so I'm just gonna, right? Given the drift B of X and the diffusion A of X and the test function H, then the potential function is uniquely defined. In other words, anytime we use a different B and A, we have to rederive these similar bounds. Now they're called Stein factor bounds or Stein factors because they are actually reusable from problem to problem. So let me remind you, right? Originally, Stein's method was conceived or came about for the normal approximation, where the limiting stationary distribution was normal. If you remember something about y0, actually the distribution of y0 is also normal 0, 1. Okay? Now, Stein factors, or the derivative bounds for the normal approximation, have been known since the 1970s. Basically, because the normal random variable is a very popular choice of approximating distribution, everybody needs these bounds, right? No matter if you're writing whatever paper you're writing on the normal, you need these bounds. So it makes sense that some people sat down and did a very careful job saying, okay, when I'm looking at a normal variable, the Stein factor bounds are this and that, right? Then for the Poisson random variable also, okay, I know Poisson is an important limiting distribution, so let me write down the Stein factors for the Poisson, for the exponential, etc., etc. So for all of these basic key fundamental distributions, Stein factor bounds exist somewhere. And also for our second and third derivatives, the Stein factor bounds exist as well. Let me give you a good reference, perhaps over here. A great textbook is by Chen, Goldstein, and Shaw. And this is 2010. I believe it's called Stein's method for normal approximations. Okay, but I'm not going to write down the name. I'm not 100% certain of it, but like there's only one textbook by this name. And in this textbook, if you want to go and follow up on the stuff we're doing today, they call this also the density approach. Basically, for all the basic or for all the fundamental canonical limiting approximations, normal, Poisson, exponential, the Stein factors are known. But they also recognize that sometimes the limiting distribution can be arbitrary, given by some arbitrary density, which is very close to our setting, right? And then their density approach talks about some generic ways to bound these derivatives. And that section of the book is what today's discussion is going to be based on. Okay. But I think giving you a reference other than these lecture notes is very important in that regard. Okay, now we're really going to go into the weeds. This lecture, for better or worse, is going to feel very low level, very detail oriented, a little bit pedantic, maybe a lot pedantic. But this is the pain you have to go through it. At the end of the day, you have to go through this pain to apply the methodology, and there's just no way about it. Okay. So, what is the agenda? We're going to talk about one-dimensional gradient bounds, the diffusion generator. I'm going to start from the generic diffusion generator, and then I'm always going to specialize to our special case so that it sticks better. We have a generic second-order differential operator with a drift and diffusion coefficient. We assume that the density exists, and the density you can find in the lecture 3 slides. We assume that H is integrable. Okay. That's again, I showed you last time in our case, the density is a Gaussian, so H being integrable is not a big deal. To save some space, I'm going to define H tilde to be the centered version of H of X around its mean. And I consider the Poisson equation. And this is where we left off last class. I gave you a lemma saying in the one-dimensional case, this thing is an ODE. I believe it's the method of variations. I think I'm not too strong on ODEs, but if you're wondering how did anyone ever come up with this form, closed form, right? It's basically basic ODE stuff. And there are two forms, number one, number two. This is, again, just to recap, the difference really is inside of the integration limits. Okay. And let me now show you, well, in our special case, I'll write it over here by the side. Again, b of x is negative mu x, a of x is 2 mu. So I just want to write out this form of the derivative so that you get a better sense for it. It'll be e negative, not negative, e x squared over 2, integral negative infinity to x, 1 over mu, negative h tilde of y, e negative y squared over 2 dy. And this, what I've written down, corresponds to the first expression. Okay. Now, it's a good idea to try and bound this ourselves before we resort to anything, any like harder or more complicated approaches. So, okay, here we have the test function h. Okay, and remember h is Lipschitz. So this object, h tilde, this is bounded, let's say, by the absolute value of y. This is sublinear. It grows sublinearly. Okay. Now, if I ignore the term outside of the integral and I focus just on the integral, and I could say, okay, let me make the integral as big as possible. Basically, if I take x to equal infinity, right? Then what does the integral evaluate to? Well, this is basically the absolute first moment of the normal distribution. And that's bounded by some constant, like I don't know, square root of 2 pi or something like that. Make sense? In other words, this integral is not the troublemaker to make this thing blow up potentially. It is this exponential, right? The bigger x is, the bigger this term. Now we hope that the size of the outside term is offset somehow by the integral, right? We only need to offset this term when x is extremely positive or extremely negative. For, let's say, for values of x around some compact set around 0, this term can be bounded trivially, right? So in other words, we need to bound to like compensate or kill this term when x is very negative or x is very positive. Now, when x is very negative, now you see why we would want to use these particular limits in the integral, right? Because there is a chance that this integral is small when x is very negative. But when x is very positive, this integral is not small. Well, it's hard to show that it's small. Let's put it that way. And that's why when x is very positive, we use the second approach, the second expression. In practice, usually it's symmetric. In other words, you can work very hard to bound this term when x is less than 0, and then all of your arguments will typically apply symmetrically, okay? Assuming that the drift perhaps is symmetric as well, but that's the main idea. So we're going to start by working very hard to bound these things. This is naive, okay? But we can say, why do we focus on the first derivative when we have the second derivative, when we need the second derivative bound? And I can say, well, just by rewriting the Poisson equation, you can express the second derivative in terms of the first derivative. And then if you bound the first derivative, you can get a bound on the second derivative. So that's some logic to do it. And indeed, that's what's going to happen, okay? But not quite. All right. Let me start with the first derivative bounds. So here, h tilde is h of x minus expected value h of y. And let me, right away, h tilde is less than or equal to absolute x plus expected value of y if h is in Lipschitz 1 and without loss of generality, h of 0 equals 0. Okay, so h is Lipschitz 1, we believe. But why is the second claim, why can the second claim be made without loss of generality? H expected value h of y minus h of x. X is in R. Well, if h of 0 is not 0, I can just recenter it, right? I can define the Poisson equation for expected value h of y minus h of 0 minus, no expectation, h of x minus h of 0. So I just recenter everything, okay? And the value of the right-hand side doesn't change. And so the Poisson equation solution actually doesn't change either. So without loss of generality, h of 0 is 0, and this bound is the important one. This is for Lipschitz, okay? Therefore, and I'm going to do this from memory, less than or equal to E0. Okay. Let's see. Yeah. 2BU over E of U, du, negative infinity x, 2 over A of x. Now we have absolute value of x plus expected absolute value of y, E0y, 2B of U, A of U, du, dy. Okay, so now I've given us a concrete problem to bound. And we're going to split this thing into two terms, namely the term corresponding to the linear expression term in x, and the term, this is like constant in x. Okay, so this is e to the blah, blah, blah. Now, negative infinity x to a of y. It should not be a of x, it should be a of y. Absolute value of x, e to negative, sorry about this. Some typos. dy plus e to the negative integral absolute value of y, which we can pull outside of the integral, roughly speaking. Okay, so this is term number one, and this is term number two. Now, let me specialize to our setting just because it's easier, and then I will come back and give you the idea for full generality. So b of x is negative mu x. A of x is 2 mu. Therefore, 1 is e x squared over 2, 1 over mu, absolute value of x, e negative x squared over 2, dy. Okay. What do you do here? You go to ChatGPT and ask it for help, right? No, but this is one of those simple ones. There's the product rule. Or even Mathematica would be good. So the product rule, and not the chain rule. Or gosh, I forgot at this point. But this is equal to, let me see my notes. This I cannot do from memory. All right, 1 over mu, e of x squared over 2, e of negative x squared over 2, and this is just 1 over mu. Okay, I embarrassingly forgot what this rule is called, but you can verify that this is satisfied. Okay, next, term number 2 is a little bit harder. Term number 2 is basically e to the x squared over 2, negative infinity x, 1 over mu, e negative y squared over 2, dy. And by the way, this is for x is less than or equal to 0. Okay, so we're just going to treat the x less than or equal to 0 part. And this is also x less than or equal to 0. Now, this is a classic bound. Why is it a classic? Because basically, if you forget about this term, then this is the probability distribution function of the normal random variable. And the question is, can we somehow bound the probability distribution function of the normal random variable, hopefully so that in the tails the bound is very small. And there's a very classic trick for this. You may or may not have seen this, but the idea is that for x is less than or equal to 0, you do the following. Less than or equal to, let me pull out the 1 over mu. I do absolute value of x over absolute value of y. Now there's no typo, right? One of them is x, one of them is y. Of course, one of them is x and one of them is y, except they should be flipped upside down. Okay, so let me slowly make sure this makes sense. When x is negative, so y is to the left of x. Y is also negative, but y is to the left of x. If we think about absolute values, absolute value of y is bigger than absolute value of x. So this thing is bigger than 1. And that's all this inequality is saying basically. Because this thing is bigger than 1, that's where the inequality comes from. Okay? Now I get 1 over absolute value of x, e to the x squared over 2 over mu. And our integral again is the same as it was in case 1. Okay, so that's the trick. But let me just write it out. Expression. We have 1 over mu, 1 over absolute value of x. This is the bound on term number 2. This is a great bound, except not so great when x is close to 0. That's okay. We can say we can use this bound for x is less than or equal to -1. Okay. For x between -1 and 0, what can we do? I will just I will show you the intuition first. For x between -1 and 0, well, we just use the worst case bound. Why? Remember from our discussion, this thing is like can be easily bounded by order 1. And this thing, when x is between -1 and 0, has a trivial bound as well. Okay, so in a compact set around the origin, we can have an arbitrarily crude bound. That doesn't matter. What matters really is the tail bound. And now with 1 and 2, okay, if you want to keep track of things, be my guest. I'm not going to keep track of all the constants because I know no matter how good of a job I do, this textbook by Chen, Goldstein, and Shell has the better constants, much better constants. Okay, but all we're going to keep track of is that there's the 1 over mu term appearing everywhere. Okay, so we've agreed. Okay, let me just finish this up for the sake of the notes. For x between, say, -1 and 0, can use supremum of e x squared over 2 integral 1 over mu e negative y squared over 2 dy less than or equal to e to the power 1 half and integral -infinity to 0 1 over mu e to the negative y squared over 2 dy. Okay. I omitted this bound. But we also need a bound on the first moment of the diffusion approximation. Okay. How you can say, okay, I know that y is Gaussian, it's normal, so then this thing is trivially bounded. But if we're not working in the Gaussian setting, what do? Well, in the one-dimensional case, you remember we have access to the density of y. So we can just write out this expected value in terms of the density and bound it that way. We can also use a Foster-Lyapunov drift inequality because y corresponds to a diffusion process, so we can obtain an upper bound that way. The point is there are multiple ways to do this. In this particular case, it's not that hard. Okay, now I want to go back. So we finished the first derivative bounds. But before I move forward, I want to say, how do you bound the generic case? Or what can you do in the generic case? Because in the generic case, right, what happens is you still have this term, term number one, and then term number two. Except in term number one, it's this exponential thing is no longer a Gaussian. And same thing in term number two. We used some tricks that were very specific to the Gaussian. Okay. Is there hope of using them again for non-Gaussian settings? Okay. So the answer is, let me show you especially the one for number two. And this is it. Let's suppose for general B and A of X, let me call this thing the ratio because it's really bulky to keep writing this out. So I'm just going to introduce R to be this ratio. And then I care about the integral of the negative ratio R of U du, negative infinity to X, 2 over A of Y, absolute value of Y. I just reminded myself that there's, of course, a typo here. And here, bear with me, please. Okay, e to the 0 y r of u du dy. And I want to show you how to do it without this absolute value of y. Right, so a lot of back and forth, but this is the term I want to focus on. Now, the idea is that if you're working with a diffusion, should it still be, so the question is, should it still be x? That h of x is less than x, where exactly? Yang. So in general, here I wrote h of x is less than x. The ones I modified were in here. Basically, anything that any variable inside the integral should be a y, not an x, because the x corresponds to the limit of integration. So any of the variables inside the integral should be y's, and I kept writing them as x's. But then the bounds here are correct. One of them is x, one of them is y. Yes, the absolute value of y, this one and this one, came from the fact that h is Lipschitz. Okay. So let me maybe say a few comments. And this is, if you're working with whatever, some exotic, super exotic diffusion process, and you say, well, how do you apply this stuff to my special case? My answer is going to be that if we're thinking about diffusions, they should be stable, right? They should be positive recurrent diffusions. What is the condition for positive recurrence that, like the Foster-Lyapunov condition we typically verify, is that there is a drift towards the origin. So my argument is that most of the time, or a lot of the time, if you plot your function b of x, it should look like this. If we are very far away from 0 on the left, we should have a positive drift. Okay? If we are very far to the right, we should have some kind of negative drift. Now, it's not guaranteed to be monotonic. Maybe it's not a linear drift. Maybe, I don't know, right? But hopefully, at some point, it is monotonic. And of course, inside some compact set, let's say negative k to k, the drift can be whatever it wants to be. So this is the general idea or understanding, and specifically, if we say focus on x less than or equal to negative k, b of x should be less than or equal to b of y. So this is an assumption. Assume that the drift is like monotonic outside of some compact set. Then what can be done? We have e to the negative r of u du, negative infinity to x, 2 over a of x, e to the integral 0 y to b of u a of u du dy. And this is using again the same normal trick, e to the negative 2 over a of x. Bear with me. Something is off. Just a second, folks. Of course, yes, this is what's off. I confuse myself. I'm very sloppy. I'm very sloppy today. This is why I was confusing myself. We have b of y over b of x, e to the integral 0y to b of u over a of u du dy. Okay, this makes sense, right? Basically, we're using the same trick as we did for the normal distribution. Now we have again this chain rule inside the integral, and this comes out to be e to the negative ratio e to the positive integral of the ratio times 1 over b of x. For x is less than or equal to this left boundary. Inside from negative k to k, again, remember that we can bound it using the crude bound. That's okay. You can say, oh, like, am I ever going to use this? Actually, I will come back to this when we're talking about the y1 diffusion. So in about 20, 30 minutes, I'll come back to this and show you that this is actually is useful. These, of course, cancel each other out, and ta-da. All right. So this is a technique for you for generic one-dimensional diffusions. All right. What about f double prime? Okay. So I just want to recap. We showed that f prime sub h is less than or equal to some constant over mu. Or I think that you can take the constant to be 3 if you're super careful, but I'm not going to worry about that. How about the abound on the second derivative? So naive approach. Just rearrange the Poisson equation. 2b of x over a of x, f prime plus 2 over a of x, h tilde of x. But this we know to be less than or equal to absolute value of x plus absolute value of y. Okay, and I just want to make sure that it is correct. Yes, it corresponds to this form. All right, now this thing is less than or equal to C over mu. This ratio of B over A, this is bounded by absolute value of X. Because in our case, B is linear and A is a constant. So what we've shown is if you apply this naive bound, you can show that the second derivative grows at most linearly. Okay. Um, is this good enough? Yes. Actually, you can make this work. If you go back, let me show the end of lecture 3. If you go back to this term and you say, okay, I've shown that f double prime grows at most linearly, then this expectation is at most expectation of the second moment. The question is, what norm is it for absolute values? This is one-dimensional, so this is just the absolute value. But in general, unless I say otherwise, it's always the Euclidean norm if I write down absolute values. So the point is, can you get away with the bound we just showed that f double prime grows sublinearly? Yes, you can, but now you need the second moment bound on x. Okay, and this is, I guess it's fine in the big picture, but if you're working with something as classical as the normal random variable, people will say, well, you're lazy because for the normal we can do much better. Okay, so let me show you. And the point of this again is if you want to go beyond the normal in certain settings, just another technique. So lemma. This is based on lemma 13.1 of Chen, Goldstein, and Schall text. Oh, it's 2011. I guess not 2010. Okay, this is, so we fix. This is an alternative representation for the second derivative. Assume that a of x, b of x or a of x, and h of x are absolutely continuous. If limit as x tends to negative infinity of this 2 okay, so if this is a super technical condition, this is just a statement about the rate of decay in the tails. Okay. Um, so basically the density has to have um, small enough tails so that this will blow up, that this term is killed, basically. Usually it's a technical condition and it's almost always true in practice. Okay. Then, so the whole thing is about an explicit expression Okay. I'm going to pause to give people some time to write this down. And this holds for all x. Okay, this holds for all x, but it's only really useful when x is negative. Once you write it down, let me make a few comments. How should you use similar expression holds with integral x to infinity instead of integral negative infinity to x? And if you want to see the full statement of this lemma, this is lemma B2 in B2 in my thesis. We're just going to focus on this thing and rough or very quickly convince ourselves that given a bound on the first derivative, we can bound everything. Okay, so the value of this lemma is that it provides an alternative expression for the second derivative, which is messier than the naive rearrangement of the Poisson equation, but actually is more powerful. It's more valuable. So let's just walk through this term by term. I'm going to copy this over, and I'm not going to write down the proof. It's just messy algebraically. There's no value, or there's little value of doing it right now. Okay. So this is my expression. All right. What do we assume? We assume h is Lipschitz, so that absolute value, the first derivative is bounded by 1. Thanks, Z, for the link. The first derivative is bounded by 1. If I focus on this term, right, it's this e to the negative integral times this thing where h is bounded by 1, so we can get rid of this, h prime, times the second e to the integral. Yeah, but we've seen this already, right? This is exactly what we were bounding in the first derivative case. So let me write here 1, 2, 3, 1, 2, 3. With, of course, 1 being e to the negative integral, negative infinity to x, 2 over a of y, e to the integral, less than or equal to c over mu. Okay, because this is as same as in first derivative bound. Okay, term number 2, maybe let me talk through it. Well, see, term number 2 involves this a prime, the derivative of the diffusion coefficient. In our special case, a prime equals 0 because it's a constant diffusion coefficient. So there is no term number 2, so to speak of. But suppose there was, okay? Well, you would need to bound this a prime, the ratio of a prime over a. And because the diffusion coefficient is some kind of explicitly known parameter, it's exogenous, right? We don't have control over it, but we know it because we derive it. So hopefully this ratio should be bounded somehow. Okay, if it's not, we're in trouble, but hopefully it is. And then we're left with e to the negative integral. Well, even if a prime is bounded, e to the negative integral, 2 over a, h, and e to this positive integral. Again, this is exactly what we just covered in the first derivative bound. Okay, so hopefully you believe me that the bound on term number 2 is not very different from the first derivative bound either. Okay, it remains to see the bound on term number 3. So f prime we bounded by a constant. That's great. The ratio b over a prime. Again, in our special case, b is linear, a is a constant, so b over a prime, that is just a constant term. Okay, so in our case, for y0, 2 equals 0, 3 is less than or equal to something like c over mu. Okay, so again, what are we doing? We use this special expression for the second derivative, and that reduces all of the derivative bounds to the same. We can show them using the same technology as in the first derivative case. Conclude f double prime is less than or equal to c over mu. And actually, this is not the best bound, but I think this is what I wrote down. So if you follow this approach, and if you want like a homework problem, try to show this bound. Okay, that's something achievable. It's not too hard to achieve. Okay. What about f triple prime? For f triple prime, let me just remind myself. Well, we've already written so much. Let me just remind myself of this rearranged Poisson equation. Okay. F triple prime is negative b 2b of x over a of x prime f prime plus 2b over a of x f double prime of x plus 2 over a of x prime negative h tilde plus 2 over a of x negative h tilde prime of x. Okay, let us again. So my goal is not to dive in and work out all the constants, but let us convince ourselves that in our case for y0, this is manageable. Yeah, just give people a second to finish writing this down. Okay, so now f prime and f double prime can be bounded by a constant. So, right, I'm just going to get rid of these, say they can be bounded by constants. H prime is H is Lipschitz, so H prime is bounded by 1. We can get rid of that. I'm going to undo all these scribbles very soon. You'll see why. In our case, A is a constant, so this thing equals 0. Not a worry there. Now, this is a constant term as well, right? Because B is linear, A is constant. So this is when I'm scribbling it out doesn't mean it equals 0. It means that it's not difficult to bound. That's all. This is a constant term, and really we are left with this thing, which is like absolute value of x. So now, remember what we talked about for the second derivative? I said we could have a crude bound, a worst bound, showing the second derivative is sublinear. Using a similar argument, we can show that the third derivative is sublinear. That's a crude bound, but actually we can do a lot better. So this is a constant, this is a constant, this is a constant. The only issue with the potential linear growth comes because the B is multiplying the F double prime. Okay, but I want to convince you that using our special form, okay, so remember how I said everything is basically boiling down to proving the first derivative? How about this? I'll leave it as a homework problem because is a little deeper. If you multiply everything by b of x, which in our case is just x, right? Absolute value of x, let's say. Then you can use this trick from the normal, I call it the trick from the normal distribution. You can use that trick to get a bound on b of x times f double prime. That is a constant of constant order that doesn't increase in x. Okay, so let me write this down formally. Let's say homework can get a constant or can bound to b of x over a of x times f double prime of x by constant. And it will be something like c over mu. No, not c over mu. This one will not have c over mu. No, it will. Yeah, whatever. Okay. This is already pedantic enough. Like this, I think this is as low level as I can go without completely boring the audience, in my opinion. But I'm going to stop here, okay? And I'm going to say, okay, remember this epsilon plus and epsilon minus terms from the fourth order Taylor expansion? So here you need fourth derivative bounds. How do you do fourth derivative bounds? You take the third derivative and you differentiate again. And you can see, right, it's already, the tedium is there because here you have 4 terms. If you differentiate again, you're going to have 8 terms, and it's just a sea of algebra. But that's what it is. Skillful execution of this algebra will get you basically a nice clean bound. A small comment. You know, at the end of the day, we're going to show some kind of rate of convergence on the diffusion approximation error. It's going to be of the form c, some constant times delta, or 1 over square root of r. The constant is never going to be sharp, okay? Because if you've been following along, what we're doing in these bounds, this is like worst case upon worst case upon worst case. So the worst case bounds, they always compound, okay? Um, yeah, I think in the application of, say, diffusion approximations of queuing models, you're not going to get sharp constants at all. All right. So let me stick the flag into the ground and say we are done. I have given you at least a believable or plausible recipe to bound the first 3 derivatives. And even though we did not explicitly need the first derivative bounds, they were needed in the second and third order bounds. Okay, we conclude that the Wasserstein distance between the Poisson or the infinite server Q distribution and y naught is of order c over square root of r. Okay, well, that's nice, but we also had y1. And remember, y1 had the following generator. gy1 f of x is negative mu x. This is called the drift. Plus 1/2 2 mu plus delta x. Also mu, if I remember correctly. Let me see. Yes. Yes. Okay. And here we'll have f double prime of x. So I want to talk a little bit about what we can show for y1. a little bit about how we do it and contrast with why not. But before we do this, I'm going to say that this is, of course, defined for x on the real line, but there is a problem with using this diffusion generator. Okay. Why? It is because the term in front of the second derivative can be negative. If you think about a diffusion process cannot have like a negative standard deviation or negative volatility. But if you remember my words from last class, there is no real diffusion process here that we're working with. We're just working with a generator and the corresponding stationary distribution. What is the problem? The problem is that the stationary distribution of y is proportional to 2 over a of x e to 0 to x to b of u, a of u du. Now, here, this term, this a will get negative as x goes to negative infinity, right? This thing is positive when x is bigger than or equal to 0. So if a becomes negative as x goes to negative infinity, this term, the integral in the exponent is going to be very, very positive. And you're going to have something like e to something very, very positive. And therefore, if we integrate this from negative infinity to infinity dx, that integral will not exist. So this is why having a negative diffusion coefficient is no good. Okay. There's a simple fix to this. I'm going to state the fix. And I guess if anyone is curious, you can always reach out to me if this ever comes up for you. Ux f prime of x plus 1/2 2 mu plus delta mu x f double prime of x. Now, if you remember, the original motivation for the diffusion coefficient was that this thing equaled delta squared times the arrival rate plus the death rate at state Q. That was the original motivation. And you can say, well, hold on. The arrival rate is always positive. The death rate is always non-negative. This thing should always be strictly positive. And you're correct. That is the case when the death rate corresponds to the state space of the Q, right? But in the state space of the diffusion, we're kind of extending beyond the state space of the Q. So it's fair to say that this thing is actually bigger than or equal to delta squared times the arrival rate plus d of 0. But the death rate of 0 equals 0. Okay? In other words, you can truncate this. Let me see the right. Let me just write this following thing. Can truncate this from below to avoid issue when a of x goes to negative infinity. And it's not really negative infinity, it's less than 0. Okay, so it's the straightforward truncation. It's a minor detail. It's not worth wasting time over it right now. Okay, but now I want to say, okay, if y1 captures the entire second order term, can I show that y1 is a better approximation than y0? And the answer is yes, you can show this. You can show actually that the distance in some special, not Wasserstein, some probability metric is less than some constant over R. Let me call this M2. M2, I believe. M2 or M3. So M2, all functions with bounded first and second derivative. So it's like the function is Lipschitz, its derivative is Lipschitz. We can show that this gap goes to zero at a faster rate. And my goal for the remaining 30 minutes is to give you the roadmap to show this. Okay. So we're going to start by reminding ourselves of last lecture. And in the last lecture, this is the generator expansion I want to focus on. We did some kind of generator expansion. We said the first order term, the second order term, and the higher order terms are third and fourth derivative related. The y1 approximation captures the entire first and second order term. So if you think about the difference, the y0 versus y1 approximation, the only term that appears in one but not the other, error term that appears in one, not the other, is this part of the second order term that we've mentioned. Okay. Now we've shown that the f double prime is like of order one. It's like it's c over mu. So f double prime is order one. The first moment is bounded by 2. We show that the absolute first moment is bound by 2. So what I have circled here is really of order delta. And delta is 1 over square root of r. We bound this from above. If we get rid of this, the hope is that the higher order terms, which are over here, they are of order delta squared, or 1 over r. And that is indeed the case. It can be shown. Okay, so lambda minus death rate, that is just the linear function. So my point is, okay, the generator minus the generator of the Markov chain minus the generator of the diffusion process is less than or equal to, it's going to be some constant like 1/6 delta squared expected value, no need for that, x f triple prime h sub x plus let's go, I'm going to say roughly delta squared f to the 4 of x. Okay, I'll talk about this in more detail. This I will brush over in less detail because there's actually, this part is more involved because the third derivative is discontinuous. The fourth derivative doesn't actually exist everywhere. But again, these are really the weeds of everything. Okay, but the highlight is that there is no second order term. And that's important. Absolute, absolute. All right, maybe I'll pause here for questions to clarify anything, to see where we're going. Whatever. Okay. So now if we replace x by the Markov chain, stationary distribution, and take expectations, what do we get? We get like two errors, 1 and 2. Error number 1, less than or equal to 1/6 delta squared, expected value absolute x, f triple prime sub h. And we say, great, well, we know that expected value of x is less than or equal to 2. It's the same distribution. That doesn't depend on the diffusion approximation. What about expected value of f triple prime h of x? Uh-oh, right? Why uh-oh? Because the Poisson equation is different. The Poisson equation is different. So you're sitting there and thinking, holy crap, now I have to go and redo all of these derivative bounds. But the setting here is a little bit more complicated. The drift stays the same. The diffusion coefficient is 1/2 mu, no 1/2, mu 2 plus delta x. And the truncation is going to be, this is where the truncation comes in. You can disregard the truncation just to make life easier. But already a of x is piecewise linear. Okay. You can disregard the truncation for the intuition, but when you go and do it, you have to do the truncation, which makes a of x only piecewise linear. And piecewise linear is not everywhere differentiable, just to keep that in mind. Okay. So with this state-dependent diffusion coefficient, if you remember one of the key terms that kept popping up is the exponential of this integral. When a is a constant, that thing is a Gaussian. When a is this linear thing, I don't know if it has a name. Wolfram alpha will give you a closed form for the integral. It's not that bad, but it becomes much more difficult to work with. So what do we got to do? We have to bound again the first derivative. And that's why I was giving you this general technique, right? We got to bound the second derivative. We have to bound the third derivative. But even for the third derivative, let me show you. A is no longer everywhere differentiable. So this thing is discontinuous. This bit is discontinuous. Okay. That doesn't kill you because if you remember our special Taylor expansion, we had the third derivative from the left. But if you want to go into the fourth derivative terms, the fourth derivative doesn't exist at a couple of points. So what you're going to have to do to bound this item number 2, you're going to have to bound the fourth derivative wherever it exists. And then at those points where the fourth derivative does not exist, you're going to get a Kruger bound. But then you also have to argue that those points are sufficiently rare that this Kruger bound doesn't disrupt your beautiful 1 over r rate of convergence result. Okay. So this is as deep as I want to go into this. Are there any questions? Yeah. Okay. So you see, it's very painful. You change your diffusion by a little bit, and you have to redo everything. That's the downside. Okay. So next week, I'm going to show you a different approach, what I refer to as the dual approach. And in the dual approach, we do not start from the Poisson equation for the diffusion. We start from the Poisson equation for the original Markov chain. And we have to get derivative bounds or Stein factor bounds on the original Markov chain potential. And you could say, oh, that seems like that makes a lot more sense in some way, because why should the approximation error depend on the properties of the limit as opposed to the properties of the prelimit Poisson equation? That's kind of one question. Anyway, this is what we'll cover next class. But in the last 20 minutes I have today, I just want to extend this idea of higher order approximations a little bit. Okay. And I want to explore, okay, we were talking about the infinite server queue. We came up with high order approximation. Anton outlined some argument that we can use to prove the thing rigorously. Is this a more general phenomena? And can we go beyond a second order approximation? What about a third order, fourth order, etc.? Higher order diffusion approximations. So going back to the, we're still in the infinite server queue model. And I'm going back to the generator. Okay, now given smooth enough function, we can do the following Taylor expansion. Sum j goes from 1 to n, basically an nth order Taylor expansion. And the error term. Okay. So in the error term, the C corresponds to the generic Taylor expansion remainder, and Fj is the jth derivative. Okay. If additionally the BAR holds, then basically what the BAR says is that, let me call this equation T sub n, sum from 1 to n, expected value, lambda plus, and I'm using capital Q to denote the stationary distribution. Negative delta n plus 1 over, so this is just the Taylor remainder term that I don't need to copy down so much. Okay, we recall delta lambda minus d of q. This is negative mu x sub q, and delta squared lambda plus the death rate is mu 2 plus delta x sub q for q bigger than or equal to 0. Okay, so for example, and this will be important to just have written, T2 says that negative mu expected value of x, f prime of x plus 1/2 mu 2 plus delta x f double prime of x equals negative delta cubed over 6 lambda f triple prime. This is the error term, so I'm gonna be a little bit imprecise here, or hand wave. Okay, that's T2, and it will be important, T3, same thing. I know a lot of writing, but we're just setting everything up. Plus 1/6 delta cubed or delta squared. Okay. So what we just did, if we look at T3, maybe let me give you guys 10 more seconds to finish writing. Okay. So if we look at T3, what we basically did is we said our Y1 approximation captures all of this circled information, and the error term is the third and fourth order stuff. Can we incorporate the third order information into our diffusion approximation? If so, how do we do it? And this is how. And then the question is more generally, can you incorporate broader information? So I'm going to call this, or let b of x be negative mu x. And this is the term appearing in front of f prime. A of x is mu 2 plus delta x. And this is the term appearing in front of f double prime. And then c of x is negative delta squared mu x. And this is the term appearing in front of the f triple prime. So in this regard, we can do c of x, d of x, e of x, f of x, right? So all of the coefficient in front of the higher order terms. We only need to work with a, b, and c. Okay? And consider the following test function. Integral from 0 to x, c of y over a of y, f double prime of y, dy. And note that, so g double prime, so g prime is just the term in the integrand, right? G double prime is c of x over a of x prime and c of x over a of x, f triple prime. Okay, so this is just a test function. Now consider T2 with g of x in place of f of x. What is T2? T2 is writing out the first and second order term and using the third order as error. Okay, so maybe let me copy this. Okay. Instead of f prime, I now have g prime. But g prime is C of x over A of x f double prime of x. And instead of f double prime, I have C of x let me write this a little different. This mu x is b of x. So let me start from scratch because this otherwise it's too confusing doing the back and forth. I've got my T2 says that expected value b of x f, this is T2, prime plus 1/2 expected a of x f double prime equals delta cubed over 6 expected value something third order. Okay, now I take this to the next page. Okay, and I use g in place of f. I get expected value b of x, c of x over a of x, f double prime of x, plus 1/2 expected value a of x, c of x over a of x prime f double prime of x, plus c of x over a of x f triple prime of x equals delta cubed error. All right, but what's going on really is that I can rearrange things. The a of x over here will kill this a of x term, and I get something like expected value f double prime of x, b of x, c of x over a of x plus 1/2 a of x, c of x, a of x prime equals, or plus 1/2 expected c of x f triple prime is equal to delta cubed over 6 expected value something in terms of g triple prime. All right, this is it. We'll be done for today. No more writing, and then maybe a quick recap of it next time. So what is going on? We picked a funny test function to do something very special. And that very special thing is to isolate the third derivative term times c of x in terms of the second and some error. Okay, now why is that important? Let me just show you. Over here in T3, we had like b of x f prime, a of x f double prime, c of x f triple prime. And with our funny test function, we've taken this c of x f triple prime and we have converted it into a term that involves the second derivative plus error. So now basically we're saying, okay, I can convert this into a second order term. Then I can use the diffusion the new diffusion coefficient to capture some of the third order behavior. Okay. And the trick we did was basically relating the third order. We're relating the derivative of a function to one higher order of derivative of the function. Okay. In other words, with this trick, we could, in theory, relate the fourth order term to the third order. Then we take the resulting third order term related back to the second order term. And iteratively, like this, we can technically relate arbitrarily high order terms back to second order. Now, of course, this technique is by no means scalable. It is a proof of concept at best, because what ends up happening is, right? So let's suppose the right-hand side equals 0, and this equals the C times F triple prime term. This thing is so messy that in any model, maybe it's tractable in the infinite server queue where B and X are linear. But in any other model, even writing down this term, even coding it up, it's very painful. It's a big pain. Okay. So, in terms of proving things, can you show that this higher order approximation decreases the error even further? I think it's hopeless. It's a dead end, especially because, as we've seen, using the Poisson equation and bounding the Poisson equation solution and its derivatives required regularity on the data. So we need C over A to be differentiable. Okay. And yeah, I think the takeaway is, in theory, you can do these higher order approximations using this idea of connecting a function to its derivative. In practice, this is extremely painful, even just to implement, to compute numerically. And that's all I want to say. In multiple dimensions, I don't know what to do. Because this trick of using this test function was very one-dimensional. I don't, even in 2 dimensions, I don't know how to derive these third and fourth order diffusion approximations. Good. So finally done. I'm glad we had a chance to segue here. All right. I'm around for any questions. Otherwise, see you all on Monday.